So here we need to find out the value of this voltmeter, that means V0. Okay, and the another one we need to find out this voltage, that means this voltmeter reading is the V minus. Okay, so we can see this is a this one is a non-inverting amplifier. This is a non-inverting amplifier, right? That means the formula will be V0 is equal to Vi1 plus Rf by R1, right? And here, what is the value of Vi? Vi is 5 volt and Rf by R1 is 10. So from here, we can easily write down V0 is equal to 55 volt. Okay? And here, due to the virtual short, you can write down this potential, that means the V plus is equal to V minus, right? So from that one, we can tell here as V minus is equal to, it will be 5 volt and V0 is equal to 55 volt, right? Now one thing, this solution will be true if there is no saturation voltage, okay? But in the question they provided V saturation is equal to plus 15 volt and minus V saturation is equal to minus 15 volt, right? Now you can see a op-amp can give maximum of plus V saturation, right? But here you can see we get the value of plus 55 volt. So let's do the simulation and see what the software give us. Okay, then I will explain you that why the software give that particular reading. We used a simulation software called Every Circuit to build this circuit. Let's simulate this circuit and observe the result. In the circuit, we can see that the voltage at the inverting terminal of the op-amp is 1.36 volt, while the voltage at the non-inverting terminal is plus 5 volt. This means that the voltage at the non-inverting terminal is not equal to the voltage at the inverting terminal, indicating that the virtual short concept is not applicable here. Let's go back to the previous slide and recalculate the output voltage and compare it with the practical simulation data. So from the simulation we get V0 is equal to 15 volt and Vx is equal to 1.36 volt. I will solve this problem and after that I will explain you the limitations of the virtual short. Okay, so how to solve this question? First, I already show you that this is a non-inverting amplifier. This is a non-inverting amplifier, right? From the non-inverting amplifier, the formula of V0 is equal to Vi multiplied by 1 plus R2 by R1. From here we can get V0 equal to 55 volt. As they provided the positive V saturation is plus 15 volt, that means the output of the op-amp cannot go beyond plus 15 volt. That's why we get the value of V0 is equal to plus 15 volt. Okay. Here we get 55 volt. That means there is some wrong in this particular process, right? What is that problem? The problem is we assume that due to the virtual short, Vx is equal to Vi. But this is not true as we are getting only 15 volt, right? So now we need to calculate the value of Vx, right, with respect to 15 volt. How we will do that one? Just do the KCL. This is, we call it point A. So applying KCL at point A, we will get Vx minus 0 divided by 1 plus Vx minus V0 divided by 10 is equal to 0, right? From here, we can write down Vx plus Vx by 10 equal to V0 by 10. From here, we can write down Vx equal to V0 divided by 11. V0 is how much? V0 is 15. So we will get 15 by 11. Okay, and what is the value of 15 by 11? This will be 1.36 volt. Now we can see our solution of V0 is equal to 15 volt and Vx equal to 1.36 volt is matched with exactly with the simulation data. Okay. So now from this problem, you can easily understand two things. One is virtual short will not work when the op-amp will work in a saturation region. Okay. This will be the limitation one. Okay. And the another limitation is if the open loop gain of this op-amp, if the open loop gain of this op-amp is low, then also virtual short will not work. I will show this case, the open loop gain, low open loop gain in the simulation. So let's go to the simulation software. We already understand the first limitation. That means if the op amp works in the saturation region, then virtual short will not work. Okay. Now going to the next one. Okay. That means the open loop gain. Okay. In my last video about the virtual short, I already explained you if we consider the open loop gain AOL in the calculation, then we can see if the gain is greater than 10 to the power 4, then we can consider virtual short. Otherwise, no, right? Otherwise, if we consider virtual short, then the output voltage V0, this one will be lower, right? Now, let's go back to the when this is 1 volt. So now you can see op-amp is works in the active region. Why? As I change the input voltage from 5 volt to 1 volt. Right? Now from the formula you can see, right, the V0 is equal to Vi 1 plus R2 by R1. Here the gain is 10. That means we will get 11 volt. So the output voltage V0 equal to 11 volt. Okay? And 11 volt is less than V saturation. That means this op-amp now works in the active region. So we can consider virtual short, right, as V minus is 1 volt, V plus is also 1 volt. That means V plus is equal to V minus. That means virtual short is working here. Okay. Now let's change the gain of the op amp. So now you can see the gain is 100 kilovolt by volt, right? That means 10 to the power 5. Okay. So now what we will do? We will change the gain and change to 10 to the power 4. Now you can see it's 10 to the power 4. Okay. Here you can see V minus is 999 millivolt. Okay. That means 1 millivolt lesser than the 1 volt. Okay. That means we still can consider virtual short. As you can see, V0 is 11 volt. Okay. And V minus is approximately equal to V plus. So no problem. So let's decrease the gain furthermore and go to the 10 to the power 3. That means 1 kilovolt per volt. Okay. Now you can see the output voltage decreased from 11 volt to 10.9 volt. Okay. And here you can see V minus, right? That means the voltage at the negative terminal of the op amp is 989 millivolt, right? That means 0.98 volt, right? That means it's less than the V plus. So here virtual short is not working as the gain is already decreased. But we can say we can still accept this situation and we can say okay, is approximately 11 volt the output voltage, so we can still consider. But if we decrease the gain furthermore, then what we will get? Suppose we will 10 to the power 2. Now you can see a drop of much higher 1 volt, more than 1 volt. So you can see the output voltage now is 9.9 volt and here is 0.9 volt. The V minus voltage is 0.9 volt, right? So now we cannot neglect 1 volt, right? So that means if the gain of the op amp is 10 to the power 4, that time is okay. We can use virtual short. If the gain of the op amp is 10 to the power 3, we can still use as is 10.9 volt. But if the gain of the op amp, open loop gain of the op amp is less than 10 to the power 3 volt per volt, then we can not use the virtuous short, as when is 10 to the power 3 at that time is 10.9, is already lesser than the 11, and when is go to the 100 open loop gain, at that time you can see is only 9.9 volt. And if we go the gain to 110 only, then you can see the voltage is only 5.24 volt, the output voltage. And here you can see the voltage at V minus terminal, voltage as the negative inverting terminal. Here you can see the voltage at inverting terminal of the op amp is 476 millivolt. That means it's only 0.74, only that means it's only 0.47 volt. And here the voltage at positive terminal is 1 volt. Okay. So from here we can easily conclude, if the open loop gain of the op amp is greater than 10 to the power 4, is greater than 10 to the power 4, then we can use virtual short. Okay. If it's less than 10 to the power 4, then we cannot use virtual short. In some examples like gate, jam, at that time they will provided the circuit with the data of open loop gain, right? At that time they can give you the value of 10 to the power 3 or 100 open loop gain, and they told you to calculate that one. Okay. In my last video, I already show you how to calculate the output voltage with the consideration of open loop gain. Okay. So just do it with the 100. Here you can see the open loop gain is 100, and here we get the output voltage V0 is equal to 9.91 volt. Okay, so let's do the calculation by our hand and see the simulation result is okay or not, or we can match the result with this simulation result. Okay, here AOL is 100. Okay, and we need to calculate V0. So V0 is equal to AOL V plus minus V minus. Okay, V0 equal to 100 1 minus V minus. As this potential will be not 5 volt, this will be 1 volt. As in our simulation circuit, we consider it 1 volt. Okay, such that this will work in the active region. Okay, so this is 1 volt. Okay, then it will be 100 minus 100 of V minus. Here V minus is unknown. Okay, so we need to calculate V minus. How we will get V minus? In this point. In this point, the value of voltage is V minus or Vx. So this point we call it point A. So applying KCL at point A, we will get Vx minus 0 by 1 plus Vx minus V0 by 10 equal to 0. From here we can write down V minus equal to Vx equal to V0 by 11. If we put this value in this equation 1, then we can write down V0 equal to 100 minus 100 multiplied by V0 by 11. So from here we can get V0 equal to 100 divided by 1 plus 100 by 11 equal to 100 multiplied by 11 by 111 is equal to how much? 9.90 volt, right? That means if the input voltage Vi is 1 volt and the open loop gain of the op amp is 100, then what is the value of V0? V0 will be equal to 9.90 volt, right? Now let's go to our simulation. Here you can see, here we give the input voltage 1 volt, open loop gain 100, so what we get? 9.91 volt. So our calculation is completely matched with the simulation. So from this video, I think you easily understand the two things, the two limitations of the virtual short. First, if op amp work in the saturation region, then virtual short will not applicable. Okay, the first one. Second, if the open loop gain is lower than the 10 to the power 4, then we cannot use the virtual short. I think by this simulation and the calculation is very easy to understand both of these concepts. Okay, thank you. Bye bye.